Welcome to your second pre-lab. Today we're going to cover a little bit more about concrete models. So this one's called Concrete Models Part 2. And in particular, today's video's goals are just to briefly review concrete models. We're going to learn about something called the solver status. And once we know the solver status, we're able to sort of gracefully catch some errors, such as a problem being unbounded or a problem being infeasible. So we can capture those so we know exactly what's going wrong if we happen to see those errors. And then we're also going to learn about how to access the decision variable values and the objective function values once we've solved our model. So we can access them via code and then print out helpful messages to the console. So let's start today by reviewing a simple concrete model. So to follow along with this tutorial, it's easiest if you download our starting file. So you can download this by following the link either in the description. Hopefully I'll get it to appear on the screen. But if you follow that link, it's going to take you to a Google Drive called Operations Research with Dr. Katie. And for this tutorial, we're looking for cslconcrete.ipynb. You want to download that file. So just download it and then save it somewhere on your computer, and then bring it over to your own Google Drive. So I think I have mine open here. So I've already, saved it on my own personal Google Drive, and from there you can open it. It might ask you to open it in Google Colab, but you'll see that this is our starting place. Now, in the rest of the video, I used a Spider IDE, so it's going to look a little bit different, but what you're basically going to do is you're going to run these first two steps, which will install Pyomo and the GLPK solver for you. I've included the original model formulation just for reference. But down here in step 3B, this is our sort of model formulation in Pyomo. This will look pretty similar to what you'll see in Spider. And then there's a few lines of code further down that solve the model. So when you need to edit anything to follow along with the video, you can just click in the code sections and edit them as needed. So this should get you all set to get started and follow along. So this is the file that we're going to go through today. So this is the CSL model. Just for a quick review, this was a model where we were trying to figure out how many technicians to hire to train each month so that we can sort of keep up with these increasing demands over time for our labor requirements. And we had two types of employees in our facility. We had skilled technicians, they know what's going on, and then we had trainees. They're the people we're training. And each of these different types of employees make a different amount of money, so skilled technicians make a lot more than trainees. Skilled technicians, when they're working, they can provide 160 hours of labor a month towards these required hours. Unfortunately, about 5% of them quit each month, and currently CSL has 50 technicians. Our trainees, if we hire a trainee, we have to train them, so they require 50 hours of a skilled technician's supervision. So those 50 hours aren't available anymore to meet these required hours for the technicians. And while they're training, they don't do any productive work. So our goal in class was to formulate a linear program for this problem to meet CSL's hourly requirements for the next 5 months at the lowest cost. So our formulation that we came up with looked like the following. We had two sets of decision variables. One was for how many technicians to train during each month, and then the other was keeping track of how many experienced technicians or skilled technicians we had at the beginning of each month. Our objective function was basically adding up all of the salary we had to pay to our experienced technicians and our trainees over the 5-month period. And then we had a set of 5 constraints that all looked pretty similar. Each of these first 5 constraints were to ensure that we met the hourly requirement for each month. So we had 160 hours times however many experienced technicians we had, but then we had to subtract off 50 hours for every trainee that we were training. And we had to make sure that that amount was more than our required skilled technician hours for the month. And then we had a second set of constraints that was sort of keeping an inventory of how many experienced technicians we had over the course of each month. And these were equality constraints, and we'll take a quick look in our formulation about how to enter equality constraints. And then our last set of constraints were the non-negativity constraints. So we can take a peek at our CSL model and see how this was implemented. So the start of our CSL file looks just like our previous models. We have to import the Pyomo libraries, and then the very first thing we do is create a model object. And specifically, this model object is a concrete model. And then we had 10 lines in this model file that were creating the decision variables. So we had 5 lines for each of our, or 5 lines, 1 for each of our trainee variables, and then 5 lines, 1 line for each of our experienced technician variables. And then you also see that within the var function, we see within equals non-negative reals. Those are our non-negativity constraints. Next in the CSL file, you'll notice the objective function. And this objective function is just using the objective Pyomo function, and then we provided an expression using the expr parameter. And we're just in that expression adding up the costs just like in our formulation. The very last part of our objective function is the sense, where we're telling Pyomo that we want to minimize this cost. Then we see our first set of constraints. Those constraints are the ones that are meeting our hourly demands for each month. Some important things to notice in this set of constraints is that we've given them nice names. So we see in line 25 that we've said that this constraint's name is month 1 demand. It's very clear what this constraint is doing. We don't want to name these constraints something like con 1, con 2, con 3, con 4, because that's not helpful when we're reading the output. Then we finally see our second set of constraints. These constraints are keeping track of our number of experienced technicians over time. And one of the things I'd like you to notice here is how we have to formulate the equality constraints. In our written formulation, we see something like E1 equals 50, but in our Pyomo formulation, all our constraints are actually logical expressions. They're being, the right-hand side is being compared to the left-hand side. So when you're doing a logical check, you actually have to use 2 equal signs. So we see that first in line 32, where our expression is model.E1 equals 50. We're not setting model.E1 to 50. That's what just 1 equal sign would do. Here we're comparing model.E1 and checking that it equals 50. It's a little bit of a nuance, but anytime we have an equality constraint, we're going to use 2 equal signs. And then finally, the last few lines of this model file are there to run the model. So first we have to make an optimizer object using the solver factory. And one of the parameters of the solver factory is which solver we're using. So we're going to use the GLPK solver. And then once we have that optimizer, we can go ahead and solve the model by using the solve function and passing that solve function our model. And then finally, model.display will display our results. So let's take a second. And go ahead and run this model. You can press play. And we can see our results over here. I can't zoom in on them, but if you've pressed play, you should be able to see them too. But one thing to notice is that, it did run. So we have values for our decision variables. We can see our objective function value, and then we can see some information about our constraints. Now, all our values were printed out really nicely, which is great. But we're going to move into our sort of next part of our lab right now, which is working with the solver status. So the first thing I want you to do here in this part of the lab is I want you to see what happens when we try to run a model that's unbounded. So the easiest way to run a model that has an unbounded solution, in this case, is to just remove some of these non-negativity constraints. So if we remove the non-negativity constraints associated with the training variables, it will basically allow the model to have negative trainees. So let's take a peek real quick at our formulation. If we have negative trainees, that's going to make our labor costs go down a lot, which is nice. If these t variables can be negative for everyone we hire, we actually will gain 50 hours of labor, so that's great. It's a little bit tricky here because if we have negative trainees, they will make our experienced technicians go down. But then you have to imagine that these non-negativity constraints aren't there. So I think overall, having the ability to have negative trainees would basically make the problem unbounded, because we want to make our costs as negative as possible. To make our costs as negative as possible, we just make our trainee values as negative as we possibly make them. All right, so here we go. So we've removed all these non-negativity constraints, and I just want you to run the model and see what happens. So come up here, press run, and see what happens with these results. They're kind of all over the place, right? Like one thing to notice is that all our variable values, they all say a value of none, 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 none. Nothing in here tells us that this problem is unbounded. Our objective function just gets this error that says error evaluating expression, no value for uninitialized numeric value object. And then same with all our constraints. We just get that sort of same cryptic error over and over and over again. What it's actually complaining about is it's saying your model couldn't be solved, so when I'm trying to access the optimal value, that optimal value is not there. But we don't know why it couldn't be solved at this point. Like, could it not be solved because we had some coding error? Could it not be solved because it's unbounded? Maybe my feasible region is infeasible, like maybe it's empty. It's really not clear. So what we're going to do is we're going to add some catches after we run the model that are going to check the solver status. So first we're going to check to see if it solved successfully. And if it did, we'll display the results. But if it didn't solve successfully, we'll check to see if it was infeasible. And if it was infeasible, we'll provide a message to that effect. And then if it wasn't solved successfully and it wasn't infeasible, our last check or our last statement will just print out whatever error was found. So that'll give us a little bit more insight into what went wrong. So in order to do those steps, the first thing that we need to do in order to access the solver status is we need to add a new import statement to our list of import statements. So we're going to add this import statement here that says from pyomo.opt import solver status, and then we also want to import something called the termination condition, because we're going to check that too. So to import both solver status and termination condition, we're just going to separate them by a comma here. All right, so the next change we're going to make is actually all the way down at the end of the model. The whole rest of the model file stays the same. And then way down here at line 41 in my model is where we're using our optimizer object to solve the model. Here, this line used to just read optimizer.solve model, but we're going to save the results of this solving action into an object called results. So you're going to want to change the optimizer.solve and then in parentheses model line. You're going to want to change that and just put results equal in front of it so that we can save those optimized results into an object called results. And then we're going to check that results object for the solver status and the termination condition. So these next few lines that you see, I know that sometimes in the videos the coding gets a little bit fuzzy, especially once they add the captions. So I've put a close-up of these. If you look in my courses, you'll see pre-lab close-up of error checking code block. This is a close-up picture of these lines if it's looking fuzzy for you. But what this first if statement is doing is it's saying, hey, if the results.solver.status, so if the solver status equals solver status.ok, so if the solver status was okay, and results.solver.termination condition, so check the termination condition, and if the termination condition was that it was optimal, so these are both if conditions, so we see this colon over here that says basically do all the lines that are indented after the colon. So if the solver status was okay and we reached an optimal solution, then I want you to display the model results. So notice that we moved the model.display . It used to be right after we solved the model. The next thing we would do would be model.display. But now before we try to display those results, we want to make sure there's actually results there. So this set of if statements is basically ensuring that there's actually some results to display. So then we're going to say model.display, and it'll print out our results if there's some results to show. If it turns out that our model status wasn't okay, or we didn't reach an optimal condition, our next else if condition is also checking the solver status, and it's checking the termination condition, and it's saying results.solver.termination condition, if it equaled infeasible, or if the termination condition was other, because sometimes infeasible models also end up with a termination condition of other. Don't forget this colon that's hanging out over here. But if we end up with an infeasible model, just print out a message that says that, hey, print model is infeasible. Perhaps you should check your constraints. So this is just a message that I wrote that'll get printed to the screen if we find our model is infeasible. And then finally, if it didn't solve to optimality and it wasn't infeasible, our else statement is capturing all the other possible conditions, and it's just going to print the solver status and the termination condition to our screen. So that can maybe provide some clue as to what's going on. So our model is still unbounded, so we can see it's still going to be unbounded because we still don't have those non-negativity constraints in here. So if we run our model now, so if I run it now, we can see that it didn't display any results, but it did display the error messages. It says, well, our status was okay, but our termination condition was that it was unbounded. So now we know, maybe we should look back at our model and see how we formulated it, and decide whether it being unbounded is a logical thing or maybe we've coded something wrong. Almost always we've coded something wrong if we find our models unbounded. All right, so for the next part of the lab, the very first thing I want you to do is put these non-negativity constraints back in. So you should put those back in. If you run the model with those back in, you should see some nice results, just like we were seeing before. Okay, so these results aren't necessarily the easiest to read. So the results that we see using the model.display function are not necessarily the easiest to read. So this last part of our program pre-lab is learning how to access the optimal solutions of our models so that we can use them within our codes. We could print out messages to the console. Later on, we'll be writing information to files. We could be doing math with some of the values that we get back. So we're going to learn quickly how to access the optimal solution values from our models. Okay, so here we see it's displaying model.results. If I want to access any of my model components' values, for example, what's the optimal value of my decision variable t1, I access it in the following way. I type model.t1, that's my decision variable's name. We can see him up here. There he is in line 9, model.t1. If I want to access his value, what I do is follow that by a set of parentheses. And this is going to access that decision variable's value. So if I wanted to, I could print it in the middle of a sentence. So I could say print by using the print function of Python. And maybe I want to say number of trainees in month 1 equals, and then I want to print out what that value is. So using the print statement, it takes in a comma separated list of objects, and my first object here is a string, and then my second object here is this model.t1, and then the parentheses say grab the value at optimality of model.t1. So if I run this now, we should see all the results displayed, and then this sentence. And if we look closely at our results over here, we can see that we're hiring 0.0 workers, trainees in month 1. So let's see if that works. Yeah, so we can see him way down here. Now we have a line that's printed that says number of trainees in month 1 equals 0.0. And I could do the same thing if I want to access what the objective function value is. I can go up here to my objective function, which I've called model.minimize labor cost. Grab that. And I might say, use my print function again and say total cost will be and then I can use model.minimize labor cost, and to access the value of that, I have to follow it with parentheses. And then this last parentheses closes the print statement. So if we run that now, we should see 2 lines. The first one tells us the number of trainees in month 1, and the second line says the total cost will be $593,000. So your job for this pre-lab is to write some statements out that tell me how many trainees I'm going to be training each month, how many experienced technicians I'm going to be having at the beginning of each month, and what the total cost will be. And just one more thing before I show you an example of that. You can also do math with these pieces of information that come out of the model. So let's say I wanted to know, how many trainees am I going to be training over the next 5 months? I could say total trainees is equal to model.t1, and then the parentheses say access the value of it at optimality, model.t2, model.t3, and then finally model.t5. So model.t1 plus t2 plus t3 plus t4 plus t5 is going to be saved into this variable called total trainees, and then I could print that out with a nice statement too. Total trainees required. We can see what that is. Looks like we're going to need 29.42 trainees. And again, we can see that we're making a linear program out of something that might make more sense to be an integer program, but for now we're going to be totally cool with 29.42 trainees. Okay, so we can take a quick look at what I did to print out those statements, because there's a couple, maybe a couple items you haven't seen before. So a couple of things that I did when I wanted to print out all of the decision variables for trainees and experienced technicians, and then the total cost. One thing that I wanted to do was, if we look over here at these results, you see how they're like really snuggled up close to the model.display results? There's sort of no space between them. I first printed this line that basically is a bunch of stars and says results. And then this \n before it is basically like hitting return. It stands for new line. And then I had one header that says CSL should hire the following number of trainees in each month. And then this \t is a tab. And then I printed the number of trainees that we need for each month. And then I did something similar for the number of experienced technicians. You'll see I skipped a line again, so we have \n, that's a new line. And I said, hey, we should also have the following number of experienced technicians at the beginning of each month. And then again, we see that each month is preceded by a \t, that's a tab. And then finally, the last item that's printed is the total cost. And here's an example where we have a string, and then we have a comma, and then we have the objective function values, and then we have another comma, and then another string. So if we run this version, we can just quickly see what those results look like. We can see this starred results line show up. We can see each of our trainees are sort of indented a little bit. Our experienced technicians are indented under the experienced technician line, and then we see our costs as well. And we can definitely get more fancy with how we format the data. So, typically we don't see numbers with 7 decimal places or 8 decimal places, but we'll save formatting for another time. So in this lab, we basically very quickly reviewed concrete models. We looked at how we can use the solver status to gracefully catch unbounded and infeasible models. And then we also looked at how we access optimal values of our decision variables and our objective functions to write out our results using helpful messages, or even to do math with some of those values. Thank you.